All right, let's get started. It's a pleasure to have Ching-An Cheng visit us today. He's a senior researcher in MSR AI Frontiers, and he got his PhD from Georgia Tech um, with Byron Boots, who's here now. And he is one of the world's leading practical theoreticians. He does some of the most interesting work in theory, which can be applied to rail systems. I was just looking at his bio. He's won all of the Best Paper Awards, including ICML, AI Stats, RSS. Pretty amazing. What I admire about his work is he's not afraid to question the assumptions of the problem. And I think he's going to tell us more about that today. And please take it away, Ching-An.
Yeah, thanks for the kind introduction and having me here. Yeah, it's my first time to speak at UW. So I graduated from Georgia Tech and never had the chance to actually study here. So in today's presentation, I want to tell you about a project that we've been working on for a year, and some very cool scientific discovery that we found, and which is very surprising to us. So the motivation or the starting point of this project is that we are asking a question, which is how we can make an agent or train an agent to learn directly from rich feedback as humans do. How can we go beyond like a numerical loss function that we engineer or reward that we kind of like randomly specify, and to directly train an agent as we train human, right? So this can mean that we want to let it learn from user feedback that will give it to another child, or let it learn directly from the console output as we are doing that regularly in our research. Or we want to kind of let it learn directly from the rich observation that the embodied agent might get. So this looks kind of like very sci-fi-like. It sometimes be the ideal thing that like we are hoping for, let's say, AGI to work on, right? But actually, right now, we are already doing that. Just that we're doing that with a human in the loop. We are the researcher or the engineer who is like interpreting those like rich feedback and then translate that into some kind of like, I don't know, new loss function, new research, etc., and tune the hyperparameter and then to train the agent in that way. So this is happening right now. So it's not really like far like away. But what is missing in how we're doing right now is that this is a very like labor-consuming process, right? We have to sit there. I mean, we run the experiments. We see how to run it for an error. I'm going to fix a bug, right? So this is how we work nowadays. So agents nowadays do learn from this feedback, but just that it's very slow and it's very labor-intense. So we are thinking about a new kind of like vision or a new kind of regime where agent can learn from this feedback in an autonomous manner, in an end-to-end manner, just like neural network can learn from loss functions, right? And now we call this approach an end-to-end generative optimization like a problem. And what it means is that we need to kind of go beyond just using gradient descent, but potentially using a generative model as the optimization algorithm. And that's how potentially we can incorporate this rich feedback and then to update the agent end-to-end in a direct manner. And so before I continue to talk about this, I want to kind of like really shout out to my collaborators, Alan and AutoDiff, who are also like equally important in this project. So this we work like equally in this project, and then that's how we kind of can build this kind of like resource and to bring our original like kind of sci-fi kind of like vision to something that's actually real right now. So the project is something that we call Trace. So Trace is a framework for end-to-end generative optimization that can allow us to train AI agents using rich feedback directly. And it's open source, and you can pip install it right now. So it's something, think about it. So there's something like a PyTorch library that you can play and then to use for your research. But it's not just for training neural networks. It doesn't require things to be differentiable. You can directly use it to declare your Python function. So all your Python function becomes like a neural network layer. And now it has a richer sense of parameters. So any Python object can be now declared as a parameter in the workflow. And now by using Trace, you can train those parameters end-to-end using rich feedback. And that's what this project is about. We are envisioning the next generation of like AutoDiff library that can train AI agents with complex interactions using rich feedback that are available to humans. So in Trace, we focus on the 3 factors that are, let's say, involved in this bigger picture. So the first one is that in order to realize this vision, we need a framework to kind of cover heterogeneous parameters, not just neural network weights, but also other things that, let's say, we are training or we are tuning using, let's say, human labor right now, right? Such as a prompt we use for, let's say, VRN or LLMs, or other hyperparameters, or even like codes that we write. So I think all these now can be viewed as parameters of a model. So we have a richer and more extended sense of what a model is. And the second bit will be we want this framework to be able to kind of consume the feedback that human uses to train this model. And so this might include some kind of like feedback you get from, let's say, recommendation, or it can be kind of like coding errors that we usually use when, let's say, doing research and debugging. And finally, we want this kind of framework to be able to kind of optimize this complex workflow in a very efficient manner. And we know that like the most efficient way we can do optimization with is trying to do this end-to-end, right? We want to kind of train a neural network end-to-end so that like every layer is considered, and we can understand so that we can better understand how the loss function and the output should affect, let's say, changes at different layers. The same goes in here. So like we have a complex workflow in our agentic system or an AI. Then we need to understand how your parameters, like a prompt, is being used in the entire system so that we can optimize it in an efficient manner. And finally, we bring all these kind of visions together and then make it into a very lightweight PyTorch-like libraries so that everyone can use it to make, let's say, our life better and can do, let's say, less engineering for your research. And originally, the reason why we are doing this is that we want to do like research on learning from a language. But we found that we don't have a very reliable and efficient tool to do optimization based on language feedback. And in all our previous projects, we ended up spending a lot of time to do engineering, and then so that we can, let's say, extract that, let's say, output from the LLM so that we can update it, etc. There's a lot of human in the loop in there. And so, but we think that right now, the technology is sophisticated enough, we can automate this and then make, let's say, training AI agent just like as simple as training neural networks. By the way, so like feel free to kind of interrupt me and raise questions during the talk. So how do we do this? The insight that we have is that we're going to challenge like an assumption that we are being taken for granted for years, which is traditionally when we think about machine learning, we are thinking about designing algorithms based on like ALU, which is a computer that can do, let's say, additions, can do math, can do logic kind of stuff, right? And then we're asking a question, what if now we have a different kind of computer, which is natural language based? So we think about LLM as a natural language computer. It's a computer that can follow logics. It's a little bit soft. It doesn't always do that reliably. But it can also understand natural languages, right? So now we have a richer set of like primitives and programming tools that we can use. If that is the assumption about the world of computing now, like how would you design an algorithm for deep learning, right? And so how would, they say, the most fundamental algorithm for deep learning, which is back-propagation, look like when we have this new kind of computer? And the funny thing here is that if you look at when back-propagation was first invented in the 80s, at that time, the computer has a memory of a size about like 100K. And this is actually the size of the context of LLM right now. So somehow, coincidentally, it's now made the right moment to think about what back-propagation might be if we have this new kind of computer. So how does we use LLM as a computer to do this kind of optimization, right? Let me give you a toy example. Suppose I wanted to update a parameter, which is to click either the left or the right of the mouse. And I want to control the mouse to kind of like, let's say, open this kind of team app. And I get a feedback about, well, you should left click on the icon so you can open it. It's probably, let's say, given by some user. So a straightforward way we'll do that will be, well, I send this feedback to the LLM and ask it to select, well, from the left or right, what is the thing you should change or you should use, right? And then probably the LLM will answer the left. But this is not a full picture of this problem because usually, for better or worse, some people like to kind of change how the keys are mapped, right? Some people let me left-handed or for other reasons, they will change the key mapping. So in this case, if the key and the left and right are actually swapped, if you ask the LLM to kind of directly output it, you're going to be wrong. So that's why it's very important to consider how your parameter is being used down the road and to do this end-to-end. And imagine now you have a more complicated like scenario where you are combining like neural network that you have trained, combining some other kind of, let's say, logics that you use to kind of like control your robot altogether, right? So if I only translate the output given to the robot to direct to the neural network, it probably doesn't make much sense. You have to consider how the neural network is used in your entire pipeline. And so that's why end-to-end is very important. So overall, Trace is composed of two parts. One is a platform. That's an infrastructure providing tools to trace your workflow, handle the backpropagation for you. The other one is called the trace optimizers. There are a bunch of optimization algorithms that are graph-based, and then that you can think about they are like gradient descent kind of algorithms, but does not require gradient necessarily. So that you can kind of switch the two. And so the way it works is that you apply Trace to trace your agent to make your workflow to be kind of end-to-end learnable. And then you provide feedback to the output of your agent's computation. And then Trace will kind of, you can now call the backward button as you do in training neural network. And now you'll propagate that feedback through the graph and to the optimizer. And then the optimizer will update that parameter for you.
Question.
Yeah.
Can the computation be stochastic?
Yes. So we have applied Trace to a bunch of applications, which I'm going to cover later on. So they can include like prompt optimization, also optimizing code together, and also like doing hyperparameter tuning automatically to optimize like, interaction between multiple agents. So to get started, let me use like example of like coding out an agent to play the game of Battleship. Right? So in here, I'm going to use the Trace to kind of like describe my agent to kind of think about, this will be kind of building the architecture for the agent. And then the agent needs to kind of like place, decide a coordinate of x, y to decide where to put the shot on the board. And then the feedback essentially will be like whether you hit the ship or not, right? And then so this will repeat for iterations. So the Trace platform is based on two primitives. One is called node. The other one is called bundle. So there are kind of like basic operations that are introduced to allow you to kind of define the graph of computation, right? So the node can declare, it's essentially declaring a node in the graph. So you can apply it to any Python object. And you can say that, set that node to be trainable by just setting the flag to be true. Now that will become a parameter. On the other hand, you can apply this bundle operator to any Python function that you write. And when you apply that, that becomes like an operator in the graph. So when you kind of like pass a node into that operator, it creates the next node. So now you can think about this function that bundle are essentially acting like a neural network layer, but it's just not differentiable. It's not based on tensors. And the cool thing is that you can also set this bundle to be trainable. So what it means is that that operator becomes like a parameter, and the thing you allow to change will be the code inside the function. So when you optimize it, the code inside your function will change in place dynamically, and you don't have to touch it again or copy pasting. So the next time you run it will be the updated version. Okay.
Are there some rules that govern the way the code can change?
So that will the code will be changed by the optimizer. So you can specify the constraint to different variables. So you can say, well, the code has to follow a certain format, etc. That can be done too. Yeah.
Can we have a specific compiler like attached to the bundle in that I want to have used this compiler specifically so that as you write the code, it can compile?
Oh, that's a very good question. So right now we don't have this feature. So right now everything is based on Python. So we're going to just run the Python runtime to execute the new code.
I see.
So going back to this example, right? So I want to write a battleship playing agent. And so I'm going to write a policy. Now this policy looks like a neural network, but it's not a neural network. So now to kind of do this forward, this policy, I'm going to think about this like a two-layer neural network. The first layer will be, I want this policy to reason about the board of the game. So I write a function called reason. I tell this is like a function that should do reasoning. But at the initialization, I just return it like a 0, 0 vector, which is nothing. So it's an empty function. And after the reasoning, I want it to act based on the plan. And that's why I write a second function called act. And in that, I just specify that you should kind of select a coordinate. This is what the act function should do. But other than that, I'm going to initialize it to be an empty function. And so this will be the policy. So when you run forward, it will call the reason, come with the plan, and then it will act based on the plan. And this is how the agent will work. But it doesn't do anything at the beginning. We just always output like an empty plan. And so when you run this agent forward, given a board of the GAN, this can be wrong. And then Trace will automatically create a graph in the backend. This is how, like how, let's say, TensorFlow or PyTorch does in the backend as well. So this will be done automatically. And now we send the feedback to the output of the computation we call backward. And now this is where there's a kind of magic. So we have a generalization of backpropagation that allows us to kind of do the backpropagation, but without requiring gradients or without requiring this layer to be differentiable. But once we have that, I'm going to talk about how this is done later on. You'll be sent to the optimizer, and now the optimizer will update the parameters, and then that'll be the next run. So in this example, we'll see that at the beginning, because I use a trivial function, it doesn't do anything. Now, after a few iterations, at the first iteration, this will get some code that will, in this game, it will actually try to enumerate the board. And this is, I mean, it kind of works. It's better than just doing nothing, but it's not very optimal. And that's kind of the plan you'll get if you ask like GPT-4 directly. But as we optimize this more with more iteration, it starts to learn a plan that can like explore the GAN and then try to exploit the known situation as well. And more importantly, this code can actually generalize. So we train on a single board, and then in this plot, we test it on like random boards that are not seen, that's not seen before, and it can generalize. And all this is done within 7 iterations. So instead of, let's say, thousands or millions of iterations as we typically need with gradient descent. So how does it actually work? How can we like make this kind of like sci-fi-like moment to be true? So we need to kind of bypass the graph has to be differentiable. And the way we do that is that rather than propagating gradients, which is not even defined here, what we are propagating is a subgraph of the graph. And we found this is going to be like a future-proof API because we found that if we use the subgraph as a way to communicate between, let's say, the agent and the optimizer, this allows us to design any optimizer that we want. So specifically, the thing we're going to propagate is something that we call the minimal subgraph. And that's the subgraph in the bigger graph that connects the parameter and the output and provides sufficient statistics to reason about the optimization problem. So there's a code, but I mean, we don't have to like, really read it. It's a recursive algorithm that runs backward, to be speaking. So at the beginning, the subgraph will be composed of the outputs. Now, every time we add the parents of that, let's say, the current graph, and then at the edges, and then we do this in an order that is in the reverse topological ordering of the graph. And once we do that recursively, we will get the minimal subgraph that's going to be witnessed by the parameter. And here's the precise mathematical definition of that subgraph. And so this can be run in a linear time, proportionally to the size of the graph. And once we have that, this is what the optimizer will see. You see the graph, and then this graph essentially documents you can think about that as like an execution trace of the process. It documents how the parameter is being used in the graph and finally creates the output. Okay.
With the gradient, I guess you want to see how perturbations in the input change your output, right?
Yeah.
Like, how does a subgraph feels like a different type, no? As in, it sounds like what you want to see is in your subgraph, if I modify a part of the subgraph, how does it change my output, no?
I think that's a very good question. So subgraph have more information than just a single instance, right? So in a graph, I know not just the current execution results, but I also know what are the functions that are used or the operators that are used in these processes, right? So suppose all the, let's say, operators are differentiable. Given the subgraph, I can literally compute the gradient.
But if they're not?
If they are not, essentially, I can reason through, for example, let's say, how this function works. Is to think about, let's say, counterfactually, what might have happened if I do something else, right? So the graph contains also the definition of those operators, too.
But for like something like a bunch of conditional if statements or something,
right.
Like something that's clearly non-differentiable,
right.
Like in that case, you just have to run forward passes through it and perturb the parameters and see how it changes.
Right, so it depends. It depends on the optimizer that you're using, right? So
you're abstracting that away from the discussion right now.
Right, exactly. So the optimizer can run in different ways. If you run in a more black box manner, you can, let's say you only do the perturbation to the subgraph, not the full graph. But you're using it, you can actually do reasoning to reason about the conditions.
Is there a constraint on, like, or a practical constraint on the size of the minimum subgraph that you can discover?
Yeah, so on this algorithmic side, it doesn't have any constraint. This is just an algorithm. You can scale to any problem. On the practical side, right now, I think the most effective way that we can solve this kind of new problem is through using LLM as an optimizer. But you know that LLM has a certain context limit, right? The larger the graph is, the harder for it to understand, or the longer you have to run it. And that's kind of practical consideration or constraint right now. So yeah, so because of this, I have very abstract and generic API based on graph. So this type of framework can allow us to kind of incorporate different kinds of like algorithms as optimizer. And so including OPRO and TextGraph, which you might have known if you're working in this field of, let's say, LLM-based optimization algorithm. In the paper that was recently accepted to NeurISC, we proposed a new optimizer called OptoPrime. So Opto is actually the mathematical formal abstraction of this problem, which I'm not going to talk about today. It's called optimization with the trace oracle. And we are showing that like for different kinds of mathematical problems can be cast in this form, including, let's say, the exact numerical back-propagation, including, let's say, reinforcement learning, learning from feedback, etc. They can all be casted as an auto problem. But that's not something I'm going to discuss today. So this algorithm is called AutoPrime. And so here's to give you some insight about how we can design an algorithm that can reason about a graph and to do optimization with it, right? Because this sounds kind of a bit too like good to be true. But here's a very constructive way to do that. So given a graph, the insight that we have is that every computational graph, because it's a directed graph and doesn't have any cycle, that graph can be expressed as a pseudocode. Basically, every operator in the graph can be written as one line of the code, and then we can like order the graph based on their topological ordering. Now we get a pseudocode that will make sense. And then we also know that like large language models are very good at doing reasoning and also like let's say suggestions and understanding coding languages, right? So you probably have been also using kind of like GitHub Copilot when you are writing code. So it's a language that you understand. So now by combining this representation, code representation with language model, we get a very powerful tool that can do optimization. This is a language that like I can understand. It can also express any kind of graph problem to optimize. So this is how we're actually doing that. So given the graph, we framed that as a pseudocode. We listed out like the definition of the operator that we are using. In trace, this is automatic grab by the docstring of your function when you decorate it with a bundle operator. We also listed like the intermediate computative value of this process, and they're all visible to the LM. And perhaps we also added like give us some memory about the past like parameter and feedback pairs. So this will go into the context of the LNs, and then we essentially ask it to say, well, if you see this like coding problem, there are some other inputs that I want to change so that my output will follow the feedback. How should I change it? And surprisingly, it can do this problem, solve this problem very reliably, even when the graph is very complicated or is, let's say, underspecified. So this is kind of very cool scientific discovery that we found. And so this is how the AutoPrime works. So here's a comparison between Trace and other kind of frameworks that are kind of popular right now to do kind of like programming or optimization based on like generative models. So one feature of Trace is that like it allows you kind of to do this in a very Pythonic way. So you can kind of decorate your function, optimize it in place rather than doing a bunch of engineering work. Because like the original motivation that we have in here is really trying to automate the entire process so that we are not just like doing the human in the loop optimization when using rich feedback. And the other kind of great feature here is that like because the way we're designing the framework is very lightweight, and it can always incorporate like more and more optimizers. Like whereas like another kind of library called TextGraph, which was included recently, like everything is bundled. Basically, you have to use the optimizer when you use that library, and you have to, let's say, use a domain-specific language to rewrite your code in order to use it. Whereas Trace is based on a very lightweight logic, which is like, well, you have your original code, let's just decorate it, and now everything can be trained. And then you can also like switch the optimizer that you want to use. You can also write your own optimizer, so the interface is clearly separated. And then so this is why I think that Trace is a very good tool for research purpose. So enough about like the technical content. So let me now show you some kind of like experimental results. So I'm going to show you a series of experiments. And the thing I want to kind of mention in this experiment is that in all the experiments, the optimizer is the same. So as I mentioned, that will going to be the auto-prime optimizer. And in all the experiments, regardless of their applications, by the optimizer being the same, it means that like when asking the LLM, it uses the same prompt template. That template is not engineered or hacked for a specific application. And this is really trying to show that now it's possible to design some optimizer that can work universally, in some sense, across multiple applications and embodiments and domains without specializing it. Whereas if you really look at the previous, let's say, papers about LLM optimizer, I mean, for example, Opera, which is one of the most famous one at the current point, if you look at how they actually do the experiments, for different experiments, they write different prompts. So it's more, it doesn't really specify the exact algorithm, but it's like a guideline to write the prompts. But now, in this experimental results I'm showing, it shows that it's now possible to really write one optimizer that can solve different problems. So in the first example I'm going to show is about optimizing the interaction of multiple LLM agents. So here we have two agents that are based on LLM. It's based on a technical reflection. They need to kind of like collaborate and coordinate to solve a household task in a virtual home environment. And so in every time step, the agent can either talk to each other. There's an action that's available to the agent, or it can interact with environments, such as, let's say, opening a door or go to the next room, etc. So these are the an action space. And so in this problem, we are optimizing the plan used by the LLM agent. So that is like a text. So in the beginning, we initialize the plan to be an empty string, and we're going to update it on the fly. And then so the graph will be about the interaction between these two agents, and the feedback that we use will be the observation of the world right now. So we run this online, and we see that like by doing optimization, the task can be solved much faster. And then in some cases, that there's also a natural prosocial behavior that emerges. So in the dishwasher task, we found that the LLM will naturally learn to talk to each other to exchange information when they don't have that, and then gradually, let's say, switch back so that it can, let's say, solve the task faster. And this is like an example to show how the plan is evolving over time when they talk to each other, but when the optimization continues. The next experiment is more like a traditional benchmark experiment. So like in prompt optimization, there's a benchmark called Big Benchmark. It's a benchmark. It's about question answering. So here we are optimizing the system prompt to an LLM and also the extractor code to the LLM. So if you have already used, let's say, LLM, you will know that when you ask it some question for an answer, it will output a lot of things. It will output is like reasoning, other kind of stuff. At the end, give you an answer. And people actually want to do that because they can, in that way, you can, let's say, get the answer more correctly. But so there's always like an extractor code to kind of extract the true answer from this, like the entire like string it outputs. And so this is the function that we're optimizing. So this is an example where we show like you can optimize both like prompts and code together, even though they are of different types. And so the way we do this is that we randomly sample some question, and then we ask this AI agent to answer it. If it answers correctly, we'll say, wow, you're doing that right. If that is answered incorrectly, we're going to provide the right answer and to say, yeah, you are wrong, you should actually answer this. So in text. So the feedback is in task. And so here the graph is essentially the logic of the agent. So in these experiments, we got an agent coded out from the DSPy library, and then we just decorate that with trace. And then we now optimize this agent to see whether we can improve its original behavior. And maybe you also compare if with, let's say, optimizing that agent using the optimizer that comes with DSPy. So the first row you see here is the base agent performance in all these questions. The second one is the agent after being optimized by DSPy's optimizer corporal. It's an optimizer that uses rewards, not using text feedback. And finally, we have this trace using the auto-prime. And we see that like the performance increased a lot. But one thing that we found very interesting is that like even you saw that these are large performance again, if you look at the learn parameters, it's actually like very like innocuous changes to the prompt. It's like it's not something that you think it will make any changes. right? So this actually shows that when you're actually using a language model, it's probably very important to incorporate some of these automatic optimization tools, because that can change the performance a lot, and that's not something that human can discover. So since it's like this is a robot like Colloquium, so I'm going to include one robot experiment that we did. It's on a simulation, not on the real robot, unfortunately. So here we are trying to use this same framework to learn a controller to control a robot to do, let's say, pick and place task. And so the parameter here is a controller code, which is written in Python in simulation. So the code will take a dictionary of the current observation about n factor location, about the object location, the goal location, etc., and a bunch of other things. And the output of the code will be essentially the delta position of the n factor, and also whether to open the gripper or not. And so that will be the code that we're optimizing, and that will be declared as a parameter. And so the workflow will be we run this agent forward in time from an initial condition for 10 steps. And then in every step, we provide a language feedback to guide its, let's say, behavior. We also, at the end, we provide like whether you successfully finish the task or not, and how much reward you get. And then we kind of do a back-propagation through time for the entire interaction that reuses this controller multiple times. So this is a controller that we initialized. So basically, we use an empty controller that always returns 0. And we just say that this is your observation will be dictionary. Your action has to be a 4-dimensional vector. And this is one of the example feedback that we give to the robot at a time step. This is automatically generated by our benchmark. But imagine that this will come from the user later on. So at the beginning, you'll see that in this GIF, the robot doesn't do anything. So this is our video showing how evaluating the learn policy on new testing initial conditions that are not seen before. So at the beginning, because we initialize the policy to be just all 0, the robot is not going to move. So after one iteration, after asking GPT for a while for this problem, how should you actually write a code? What it will do is that it will write a code to directly drive the robot on to the goal, but it doesn't know whether it has to pick up that object and then put it there. And so after a few tries, the policy will learn that, yeah, it has to pick up the object because of the pick and place task. But it doesn't really know when to release the object and to drop it. But after a while later on, it will learn to have this very complicated policy, which actually look like this. So it has a bunch of like triggering conditions to learn when you should approach the object, when you should grasp it, and when you should, let's say, move it to the goal, and when you should release. And this policy gets 100% success rate.
So is the corrective feedback generated through like simple, let's say like snap planner controllers, or what are you using to give the
Right. So in this benchmark in particular, we have an extra policy. That's how.
A ground truth policy.
Yeah, it's not optimal, but it's a scripted policy that comes with Meta World, and we are using that as part of the thing we use to synthesize the feedback.
Like as an oracle.
Yeah.
Okay.
Yeah.
And then just to be clear, you did not do anything for the reward model, right?
No. So it doesn't. The information it sees in this training kind of loop is feedback like this about like it tells you like whether you did what you did is like correct or incorrect, like why that is the case. It will make some suggestion about what you should do next, and then whether you should, let's say, open or close the gripper.
I guess what happens if you also set up a reward model that just start returning 0, and then you also does optimization?
Right, I think that's a very good point. I think in this experiment we are not using RL, etc. So we're directly asking the optimizer to change the code. The only information about reward you receive in this problem is that at the end of the episode, there's one more feedback that tells you how much reward you get in this episode. So there's some information about that and about success rate at the end of the episode when we do the backpropagation.
In the feedback, it says the reward was.
Right. So that's also like appearing in there. So the original meta world environment comes with a reward, and that's a number that we're reporting as part of the feedback. Okay. Sorry. Yeah.
Could you go back to the previous slide?
Yeah.
Wait, just to confirm, the numbers that you see there, those were created by the model, or?
No. So you mean in the feedback?
Yeah.
Oh, so those are the created by the expert policy that we have. Yeah.
Okay, nice.
Yeah, so in this kind of like robot, there's no model in the robot. The robot is controlled by the Python code like that. And we are providing feedback to the robot, and then so the optimizer essentially translates those feedback into code updates in place. Okay. So there are two more examples which are not really done by us. So done after like Trace was released. So in this example, they are using Trace in a very novel way that we didn't anticipate. So they are using Trace to kind of like optimize the code, the mapper code used in parallel programming. So which is about like allocating resources there. And they found that like if they train that code using like feedback, and it can in like less than 10 iterations, it can surpass the performance of an expert code that, let's say, domain-specific expert write. I'm not an expert in that domain. I don't know what that is. But I think this is a very cool finding to say that like this can be a very powerful tool, and then it's only up to your creativity to decide how to use it. The other kind of like example was also not done by us. It's done by like a summer intern playing with Trace. So he was trying to see that whether Trace can like jailbreak a language model safety guard, and it actually can be done also in a few iterations, which is actually very concerning. So in this example, like he's trying to train a prompt so that like GPT-4 under the safety guardrail can answer some question that is not supposed to answer. So I'm giving one example here. So here he's asking the GPT-4 to write a code that can erase everything on a computer. And so GPT-4 will refuse to answer that if you try it. But here we are training, like using another GPT-4, which doesn't have the safety like guard, as an optimizer. And after 6 iterations, it will trick the ideally to be safe GPT-4 to answer that question. So we also try other kind of like more sensitive question, which I don't list here. It will work, but this is a very concerning potential thing about using this in your application. So, but it also shows essentially how powerful this framework can be. Yeah. So as a summary, like here we are with Trace, we are providing and also proposing a new kind of like perspective on machine learning and optimization. And we are calling that end-to-end generative optimization, which is a technique that optimizes the entire workflow end-to-end, which might not need, let's say, gradients or needing the workflow to be differentiable. And the way we are doing that is that like using generative model as part of the optimization algorithms. So right now we are using like LLM mostly, GPT-4, but like we are also working on potentially using, let's say, a vision language model to do the optimization, right? And this can also go beyond like the text domain to be multimodal. So on the Trace design, in the infrastructure, there's no limitation on what kind of model you can use or what kind of, let's say, workflow you can trace. It can be multimodal. It can use images and videos, etc. There's no restriction on that. So you are free to play with that. But right now, our experiments are limited to text spaces of like optimizing kind of of workflow that can be expressed in text in a compact manner. And the results kind of show that like now is doing kind of designing optimizer to do this kind of like learning from or optimizing from language feedback is kind of like something that is possible, but I think there's a lot of things that can be done there. So I really want to highlight that what I've shown right now is just like the very start of this new field, which I think will be very, very cool. And the way I want to kind of like make the knowledge is that I really think that what we are seeing here is that like Trace is providing a platform, kind of like a PyTorch. But the algorithm that we are running in all this application is kind of like a vanilla gradient descent algorithm that I think no one will actually run in your own kind of research or project, right? So we are using probably like Adam, Adagrade, or RNS, whatever, out there. But I don't think the algorithm that we are seeing in this generative optimization is at that point yet. So there needs to be a lot of research to be done to think about how we can design optimizer that is more adaptive and more robust and to scale with different kind of workloads. On the other hand, I think there's a lot open space to discover new applications if we adopt this mindset of like end-to-end generative optimization, right? What are the new scenarios that we can build right now, and which might traditionally requires a lot of like engineering or human in the loop, which is like time-consuming. But now everything can be automated with like a very simple API, just as you would, let's say, train your network, right? And so, and that's also a very exciting direction. And so to conclude the talk, I really want to mention like an aspiration. So we have seen that how AI has evolved from the 60s when we have like just a perceptron to now we have a language model. So we're thinking about, well, what does it take to go to the next human level, let's say AGI in the future, right? If you look at the past, how the way we create the next, let's say, breakthrough in models is usually done by some breakthrough in the optimization algorithms. So at the beginning, we have SGD. That's how we have perceptron. And then we know kind of like we can do back-propagation. That's how we actually have content. We have like we can CNN, right? And later on, we have like PPO. And that's how we start to have like language model, et cetera. So every time there's a breakthrough, something cool will happen on the model side. And we're hoping really that like Trace will become like the driving vehicle to enable that breakthrough. And I think the breakthrough will probably be done by you because we really need new algorithms. And to this, I will just end my talk and want to answer any questions that you have. Yeah. Okay.
Yeah, that was a very nice talk. So one in robotics, right? Like people usually talk about how like these large models are always calling APIs.
Right.
Like for some, and it's assumed that like the API will just solve a task, right? Like,
Right.
But if you actually want to train like lower level stuff, then that
Right.
involves like probably RL or like
Right.
doing a lot of hyperparameter tuning
Right.
and like. I'm curious if you see this as a way to also kind of like hyperparameter tuning to learn those low level like
Right.
functions that are not possible yet.
Yeah, I think what you're talking about, I think there are two parts. One is about, well, if I have a very complicated thing with low level, high level, is that something that a single API code can address? Right? I think that my answer to that will be no. It's like the LLM is not like a god. It can answer any question that you ask it, right? But it does answer, I mean, some questions very reliably, and that's why we need to break down the problem. And then so I think in this bigger picture, there is still an element of designing the architecture, which is designing what the graph is, what needs to be trained, what is kind of like already like structured and it already can be known, right? And then also like what kind of information you should use to train each part. I think about the low-level training part, I think for let's say, I'm 100% sure that say LLM cannot output, let's say, the weight for a neural network. You cannot say, well, give me the weight for, let's say, the two-layer neural network so that you can, let's say, let's say control this robot. It's not going to work, right? But it does not understand some kind of low-level code. So we have found experiences that you understand like code in the C++ level in some numerical arrays. That's fine. So I think to use this to your advantage, it's really up for you to really think about what is the abstraction, what is the architecture that you should use, so that like you can build a system that you can really be empowered by the use of LLM.
Pretty cool. Thank you.
Yeah.
So like with regards to the optimization
Right.
algorithms you're talking about, so it seems like the insight is that you can, like with that computation graph, you can, if you select only the subgraph, you're basically rearranging the sort of information in the prompt to be more efficient so it can reason about it better.
Yeah.
So when you talk about like, improving the optimization process, does that come for free with like language models improving in general, or do you think you have to do something more clever, or is like in your mind when you talk about improving, like something more clever with how you feed that information to, let's say, the LLM optimizer?
Right. I think that's a very good point. So I think the optimizer, on the one hand, will naturally improve when you have more powerful LLMs, right, which can reason and understand more complex stuff. So that's one like driving force. But I really think that there needs to be an algorithmic design or like innovation there. I think, for example, like the way we're doing here, which is I dump the entire thing in a single query, it's not going to scale for very large graph. Right? Potentially, we need to, let's say, the graph is available to, let's say, the algorithm designer as a data structure. We can design essentially how to kind of like do the abstraction of the graph and potentially make multiple queries. Now people are working on like multi-agent systems, right? You can think about like you have a graph problem. Now you separate that workload into multiple agents. I think it's also very important to think about that how can we combine, let's say, traditional search or planning algorithm as an optimizing algorithm by also using LLM as part of the loop, right? But not entirely. So I think a lot of things will happen not just because LLM is like updating, but because we're designing better algorithms.
This is like pretty great talk and a great way of thinking about like abstracting the problem. So in the in one example you had like these functions for like reasoning and acting, or you could like as a designer have like multiple steps to like based on your abstraction. Suppose as a designer you make some mistake in the final code, like acting is like reasoning 1, reasoning 2, reasoning 3, reasoning 4, and then you do some action based on it. Suppose you by chance forget to write something, like you comment out one reasoning step in that. In this system, like does it throw that error, or is it able to understand that some part of the computation is like not given by the human itself?
Right. So that's a very good question. So so right now, what's very cool about like Trace is that like every execution error that happens at runtime, it will be caught automatically by Trace. And then that can be used as a feedback to send to the optimizer to directly change the code. So in the battleship example, what happens when you actually run it is that like because when we write the code, the agent doesn't really the optimizer doesn't really understand the API of this battleship again. So it actually will make like write code that doesn't satisfy the API, and it will return an error. So but then it will use that error as a signal to in place update those codes on the fly. So you will first basically learn to use the environment, and then you will learn a strategy that can kind of like, let's say, do better. So this can be done automatically without, let's say, us to stop the program and then kind of like inject other things.
I think this is a really, really cool thing. So I'm just wondering, how do I play around with this?
You can pip install, right? I show you. There's a link. There's a link, which is the link to our web page. But now you can just pip install it. Yeah.
I'm trying to compare what is doing automatically with me copying a code template and pasting to GPT. I just generate one and copy paste it back.
Yeah.
It works very well in many cases where code is well structured and the input output is well defined and the code doesn't depend on overall context.
Yeah.
But sometimes the code depends on some design decisions you made out of context, and in those cases GPT tends to generate some code that's not desirable and can be desirable unless you tell you like unless you paste like the whole project into GPT or you exhaust the whole context of GPT. I wonder what kind of thought you have.
Right. So I think there are kind of two things that are related to what you're talking about. One is that like when specifying something as a parameter, let's say the code, you can also specify constraint in natural language, right? You can restrict it to, let's say, write code in a certain way. So you can provide those hints, and you will see that as part of the context. But the other thing is that I think the idea that we are trying to propose here is that it's not trying to do this in zero shot. It's like I phrase the question, and then ask it to output the right code in zero shot. We are thinking about this. I mean, LLM is not basically in our understanding, like LLM is not good enough for that for very complicated things. But they can be used reliably as an improvement operator, right? Given the current thing, well, if it doesn't do what you want exactly, it provides feedback. It knows how to incorporate those feedback and improve it further. But that being said, in the other experiments, I think like if your code requires, let's say, using a lot of external libraries, which doesn't have, let's say, which is like custom to you, which is unknown to the language model, and I don't think that will work pretty well. Because they probably need some way to kind of provide information about what are the things you can use, how they work, etc. And that's a real issue, because otherwise you can say that, well, I just have one code, which is my entire project. Can you write it for me? Right? This is not going to work. So right now, this is for optimizing certain code segments in your bigger like workflow.
Thank you.
Go ahead. Megan?
This is perhaps a different question along the first part of the talk. Have you encountered any situations where Trace itself tried to put out an alpha, kind of like how, for example, NVIDIA Lyrica tries to give reward functions on top of which RL can be run? Has anything similar been done with Trace, where like part of the code is done as part of an ML optimization, and then the rest is optimized by LLM?
Oh, you're saying
LLM outputting.
Are you saying that like is any part of the code of Trace being done by Trace, or what's your question? I don't fully follow.
As in, does Trace ever itself put out an ML training pipeline, or could it work with? For example, if I asked like, oh, here's my network, and here's a code that trains that network and then tests it.
Right. So
you try to change the architecture so that it works.
Right. So in the official experiments, we didn't do anything like that. But when we were playing around with that, we did try to use Trace to kind of like say trace ML pipeline, and it works. So it can, because it's very flexible, you can declare anything as an operator, right? So I can have an operator say train this part, and so it can trace that, and then we have some tutorial. We also have a one that automatically tune the hyperparameter of an ML pipeline. So basically we do that, and then we see validation. We use that as like the feedback, and then it gives you like a very lightweight tool to directly do auto ML without like specialized tool.
Question on that front, like
Yeah.
when you're doing this AutoML pipeline,
Yeah.
what is the rich feedback that you feed back in?
Oh, so there is not super rich. Basically, we are saying by tracing it, the optimizer knows that this like graph is about optimizing some neural network with some data, right? So this is like known to it.
So it's no better than any other AutoML pipeline.
Yeah. So we are not comparing. So this is why it's not like something we actually seriously studied before. And the feedback output is not rich. It's just that we're saying, well, this is a training loss, this is a validation loss, and then but I can't understand it because I feel like everyone has been trained on this kind of information.
But I mean, I kind of have a question about using LLM as an optimizer. So I mean, realistically speaking, we cannot guarantee convergence, right? So, and then it gets worse when we have multiple neural networks or computational graphs that depends on the optimizer.
Yeah.
So how do we check when we actually optimizing using natural language? Can we actually see the feedback, and then depending on the feedback prompt, the optimization path would be different, right? The landscape of the graph is different.
And that's a very good question. So I don't have an answer to that. I think that the theory for this is open-ended. I think in the paper, we have a very long like appendix to even discuss like in this kind of problem, what is the solution? Like what is the solution concept when we are talking about an optimization problem based on feedback? There is no objective. I cannot even say there's an optimal, right? So we have a more like a philosophical discussion about how do we even like discuss and begin to define what the solution is before we talk about complexity.
Have you compared like the Atom optimizer and then your natural language optimize and then see how close they are, like absolute neighborhood kind of thing?
Right. I have one slide for that actually. So in one of the experiments that we show in the paper, we're comparing this with, in doing numerical optimization, here. So we randomly, wait. So we randomly generate. Yeah. So we randomly generate some like math functions. We have a bunch of like math operators, and they are differentiable. So we create like a 1D function, and then so we randomly generate that, and then we use like PyTorch add-in to optimize it. So that's how you get the training curve in there. On the other hand, we do the same thing. We provide a feedback about whether your output should be larger or smaller, and that's essentially like the L1 gradient for the L1 loss at the output. And so we found it's kind of converging similarly for small problems.
So like what portion of, I guess, all of the tasks you've sort of looked at using this LLM as an optimizer framework, fall under fundamentally using like binary feedback signals? Like, would you say it's?
I would say very little.
Okay.
I think usually, so let me give you an example which I didn't show in here about failure case.
Yeah.
So for example, if I wanted to use this to optimize a prompt to an LM, and all I give as a feedback is whether it works or it doesn't work as a binary feedback. What happens is that you will see the GPT-4 inside the optimizer will refuse to respond. It will say, I don't have enough info. I really don't know what you want. And then so it will just like just doesn't make any changes. So I think in this framework, the more informative the feedback is, usually the more like human-like or like the more it closest to like the raw source, or even the most constructive it is. Just like think about, let's say, the feedback, let's say your advisor might give you, right? If that's just like, well, you failed pass, probably it's not very informative. It has to be more constructive. so if they are constructive, usually it works pretty well.
So it's fair to say it's like you want a kind of a hard yes or a hard no followed by an explanation. Yeah.
Exactly.
This is with respect to the optimization stuff you were asking for again. You're saying that using this framework, it's like vanilla gradient descent, and you have some other optimizers like Adam and Adagrad, which will like maybe use some part of the past observations to like smooth out some of the landscape or like have some momentum. What do you think that looks like when you're using language as an optimizer? Like, what does adaptive optimization mean?
Yeah, that's a good question. I don't have an answer to. We have some preliminary attempt. So basically what we're doing, let's say in AutoPrime, there's an option for like adding a memory to that. So what it does is very, very, very like vanilla, which is in addition to this kind of other kind of problem, we also provide it with kind of like pair of the previous parameters and the feedback it received. And so as an in-context example for you to understand like what kind of parameter will receive what kind of feedback. We found that it helps stabilizing in some harder problems, but that's usually not necessary for simple problems. So yeah, so I don't have an answer to your question, which is I don't know what it has to be adaptive. I mean how it can be adaptive, but I do see that like right now this optimizer is not going to solve for all the problems, and then so this is why I feel like this really needs to be done.
I think we're out of time, but yeah, let's thank Ching-An.